Have you ever wondered why bending moment diagrams are drawn upside down? Take a simple beam with a point load at midspan. We solve it using the method of sections. The mathematics is straightforward. The moment function increases linearly from the support to the center, and then decreases linearly back to zero. The graph is a triangle, exactly what the equations predict. A perfectly reasonable triangle. Its base is at the bottom. Its peak is at the top. And then we are told to flip it. Now the peak is below and the base is above. Why would engineers do that? Maybe that was just a special case. But then we try a uniformly distributed load. Again, we solve the beam using the method of sections. Again, the mathematics gives us a perfectly logical result. A downward opening parabola, a shape that follows directly from the equations. And then once more, we mirror the entire diagram. The sad parabola becomes a smiling one. At this point, most students stop asking questions and simply accept the convention. But there is actually a very good reason for doing this. The answer is that the bending moment diagram is not drawn this way for mathematicians. It is drawn this way for architects and engineers. Its purpose is not only to show numerical values, its purpose is to help us understand the structure. And to do that, the diagram must tell us something about the way the beam behaves. To see this, let's perform a thought experiment. Imagine that our beam, the one with a point load at its midspan, becomes more and more flexible, until eventually it loses all resistance to bending. At that point, it no longer behaves like a beam. It behaves like a cable. And that cable will help us understand the strange convention behind bending moment diagrams. Let's see how this can help us understand why a perfectly good graph gets flipped upside down. Imagine a laundry rope stretched between two supports. Now hang a heavy boot at its center. What shape will the rope take? And what if, instead of a single boot, you drape a sheet along the entire rope? What shape will the rope take now? Take a moment and make a guess. Let's start with the boot. When the boot is hung from the laundry rope, the rope takes a triangular shape. Now look at the bending moment diagram of the beam under the same point load. It is also a triangle. The rope and the diagram have exactly the same shape. Let's move the load. Suppose we move the boot toward the right support. The rope immediately changes shape. One segment becomes steeper. The other becomes flatter. Now think about a point load on a beam. When the load moves, the bending moment diagram changes in exactly the same way. The peak moves. The slopes change. The entire shape adjusts. The rope is not merely similar to the bending moment diagram. It behaves like the bending moment diagram. Now look at the sheet. The rope forms a smooth parabolic shape, and the bending moment diagram for the uniformly distributed load is also a parabola. Again, the shapes are identical. Not similar. Identical. So let's return to our original question. Why do engineers flip the bending moment diagram? Why not leave it exactly as the equations produce it? Because the mirrored diagram is much easier to interpret structurally. Once it is flipped, we no longer see just a mathematical graph. We see a shape that immediately tells us something about how the beam wants to deform under loading. Now, let's turn this idea into a practical rule. When reading a bending moment diagram, first look at its position relative to the x-axis. Is it below the axis or above it? If the diagram lies below the axis, as in a loaded simply supported beam, the beam tends to sag. The bottom fibers stretch. The top fibers shorten. So the bottom of the beam is in tension, and the top is in compression. This gives us our first reading rule. A bending moment diagram below the x-axis means tension develops at the bottom of the beam. Now, let's look at a different beam, a cantilever. Here, the rope analogy no longer helps us, but the rule remains exactly the same. The bending moment diagram lies above the x-axis. The beam tends to hog. Now, the top fibers stretch, and the bottom fibers shorten. So the top of the beam is in tension, and the bottom is in compression. This gives us our second reading rule. A bending moment diagram above the x-axis means tension develops at the top of the beam. The rope helped us discover the convention, but the convention itself works for every beam. One final observation. Some beams contain both types of behavior. The bending moment diagram may cross the x-axis and change sign. In those cases, the rule still works perfectly. Where the diagram lies below the axis, the beam tends to sag, and tension develops at the bottom. Where the diagram lies above the axis, the beam tends to hog, and tension develops at the top. Notice that we are not trying to predict the exact deformed shape of the beam. Instead, the bending moment diagram helps us identify how each region of the beam wants to deform. And that is often the most important information for understanding a structure. So the next time you draw a bending moment diagram, don't look at it as just a graph. Look at it as a structural sketch. It shows you where the beam tends to sag, where it tends to hog, and which side is in tension or compression. Once you learn to read it this way, the bending moment diagram stops being something you simply calculate and becomes a tool for understanding the structure at a glance. If this video made something that once felt arbitrary suddenly make sense, that is exactly what Physics and Structures Made Simple is built to do. Not just teach you which formulas to use, but help you see why structures behave the way they do. So instead of memorizing one procedure after another, you begin to understand the logic behind them. And once the logic is clear, structural analysis becomes simpler, more intuitive, and much easier to remember. If that's how you want to learn structures, the full course is waiting for you. The link is below.